You're given two sorted arrays, nums1 and nums2, of sizes m and n respectively, and we want to find the median of all the numbers in those two sorted arrays. And it needs to be done in time complexity that's log of m plus n. So for example, if the two arrays that are given to us are uh, this two element array 1 comma 3 and this single element array, then the median of all the numbers combined across these two arrays clearly would be 2, because the three numbers are 1, 2 and 3. The median is defined to be the middle number if we have an odd number of elements. So if there is an odd number of elements, we will have a unique middle number, and that is clearly 2 in this example. If we have an even number of elements, like in the second example, then when we look at these four numbers in order, it's 1, 2, 3, 4. There is no unique middle element, but we have two middle elements. And the median is then defined to be the average of those middle two numbers. So 2 and 3 happen to be the middle numbers in this example, and so their average would be 2.5. So that's the expected answer. And in example 3 here, all the four numbers are 0, so there can be duplicates. And if there are duplicates, the semantics is still the same. If you look at the numbers in sorted order, the middle number or the average of the two middle numbers would be the median, so that would be 0. If there is no um, number in the first array and there's a single number in the second array, then the median is, again, you have to combine the numbers in both arrays. There would be a single number, and so the median would be 1. And it's possible the second array could be empty, the first array could be non-empty, in which case the single number would be 2, so the median would be 2. So a brute force approach, if we begin with a brute force approach to solve this problem, a brute force approach, as you recall, is an approach that is either exhaustive or it's something that follows directly from the statement of the problem. So in this case, we don't have to be exhaustive, since from the statement of the problem, or we can say the definition of median, we know that the median is the middle number when all the numbers are sorted. And so a brute force approach would uh, compute the median as the middle element after combining the two sorted arrays. So find the middle element, or uh, it could be one or two elements in the middle. Um, find the middle element of the combined sorted list of numbers. So that's the definition of the median. Now, how do you get an overall sorted list of all the numbers? So we have two distinct arrays given here. So we can combine them by merging them together. Since they are already given to us to be sorted, we can merge the two sorted arrays. We know how to do that in order m plus n time. That's exactly what we do in merge sort. And after merging the two arrays, so this would require auxiliary space. After merging the two sorted arrays into a single sorted array, we would do an index lookup. Either look up the unique number in the middle, or look up the two numbers in the middle and then compute their average and return their average. So in terms of time, we know that merging two sorted arrays requires order m plus n time. Index lookup requires constant time. So the total time required would be linear according to this approach. So you could argue that we don't need to merge the two arrays completely. We could we could bail out once the median is finalized. So we could do the merge only until the median is finalized. But that just means we merge the first m plus n by two numbers or so. That wouldn't change the asymptotic time and asymptotic space. But that wouldn't change the asymptotic time complexity. And so our goal is to do this in logarithmic time as the problem has described. So either order log m, or you can say order log n, assuming the two arrays are of lengths m and n. So they have specified that clearly. In fact, it's not even a follow-up question here. They have specified it directly as a requirement. So when you have two arrays in this case which are already sorted, and you see logarithmic time, you would assume that this probably needs to be done using binary search. And if we had to do binary search, we could ask on which array. Well, there are two arrays, so we always do binary search on a single array. So do we pick one of the two arrays arbitrarily? We don't know if binary search will work, but if we had to do it, we have to decide which array we want to do it on. It's possible that it doesn't matter because the time requirement for us is that it should be logarithmic in the sum of the lengths. If we had to be nitpicky, you could say that between log m and log n, we would prefer the array which has a smaller size to do binary search on. So if we had to be really nitpicky, we would pick the smaller array to do binary search on, hoping that each step will need only constant time. That's how we get that logarithmic complexity. For our purposes, we'll just assume that m is less than n and just do a binary search on the first array. That's the plan. So so this is the setup of the problem. Are there any questions on the what we will be attempting to do? The details, whether binary search will help or not, that is something we will look at. But the direction in which we are going is going to be binary search. So, any questions about the problem statement or any ambiguity about the examples? You can just raise your hands if you have questions. Pratik?
Hey Omkar, just for clarity, when we say could merge only until median is finalized, do you mean to search the first half of the array because it's sorted, so we know that we don't have to traverse beyond n by 2?
Yeah, so as you know, when you merge two sorted arrays, we we use a decrease and conquer approach where we just decide what's the first element going to be in the merged output. So we pick the element at the head of the two lists. Then we repeat the same thing in the remaining list of remaining list of numbers, the two lists. Again, pick the smaller among the two elements. That would be the second number, and so on. So once you have, you know how many numbers there are, it's m plus n. So once you have the first half of the uh, list, right, m plus n by 2 numbers merged, you know that the last number that you picked, or the last two, uh, they would define the median, and so you can stop there. But it would just save you a constant factor of 2. It wouldn't it wouldn't change the asymptotic complexity.
Right, got it. Thanks.
So I just want to take a poll before I because when I solved it, I was looking to see if, how other people have solved it, and for I couldn't really find this solution online. So just and somehow the solutions that I saw, I checked out one or two videos and lead code discussions. I couldn't really, I didn't really find them very easy to understand. So how many of you have solved this problem and understood the solution? Just curious if you can raise your hands out of 41. Okay, only three of you have. Four. Yeah, Raghu, obviously. Four of you have solved this. Four or five, maybe. So, uh, how many of you have tried it but not been able to solve it? If you could just lower your hands, those who have solved it. How many of you have tried this and not been able to solve it, or not understood the solution? Only five, uh, five, six or so. So the rest of you haven't tried. So I guess you're not looking at the highest frequency questions, I assume. So um, anyway, so this is among the top five. I think this is the only one among the top five that I have not covered in my classes. So let's see how to go about doing this. So um, when I'm going to go through the process that I followed uh, in solving this, and you could have, if you've solved it, you could have followed a different process. Um, you might recall from the sorting live class that um, we found the algorithm. We found a single algorithm, I should say. We found a single algorithm for finding the median in a single array, which was not sorted, as well as the kth smallest and the kth largest elements in a single array that was not sorted. We found a single algorithm for, I should say, the kth smallest, median, and kth largest element in an unsorted array, right? And that single algorithm was randomized quick select. So we didn't try to design an algorithm specifically for the median. We solved a more general problem, and if we could do it for a general kth smallest or kth largest, then all we had to do was to put k is equal to n by 2, or n by 2 plus 1 or something like that, and get the median. So here also we will find we will try to we will design, I should say, a single algorithm for finding the kth smallest, median, and the kth largest number in two sorted arrays. So just trying to point the relationship here in a single unsorted array. That's what we did in the sorting class. Here we have two sorted arrays, and we'll try to solve a more general problem. And if we are able to design this algorithm, then um, after that we can let k be equal to some specific index, and I can't hand wave about it for this problem since we have to execute the code. So let's think about so let's say we will focus on finding the, in general, the kth smallest element in two sorted arrays. Right? If we can do that, then we can substitute k equal to some specific index and get the median. So what will that index be? So let's say m plus n, suppose m plus n is odd. Okay, there are two options. Um, if m plus n is odd and if m plus n is even. So when I say kth smallest element, how do we define it? Again, in the same way that we had defined it in the sorting class, if you were to have all the numbers sorted, then k tells us the rank of that number in that sorted list. So the first smallest, if k is equal to 1, we get the smallest number overall in that, in those lists combined. If k is equal to 2, we get the second smallest, and so on. So if m plus n is odd, for example, if m plus n is, let's say, 7, right? If we have 7 numbers in sorted order, we know that the middle value is going to be the fourth value. Right? If we have 3 numbers in sorted order, we know the middle value is going to be the second value. So you can see a pattern here that if we have m plus n values and m plus n is odd, just like if m plus n is 7, if I divide 7 by 2, this is integer division, so I'm going to get the, you can say, the floor, or so this will be an integer result. So 7 divided by 2 is going to be 3, but I really want the fourth value, so I'll add a 1. And if m plus n is even, let's say m plus n is 8, then I want the fourth and the fifth values. Those are the two middle values. How do I get 4? I just divide 8 by 2 and I get 4. So in a similar way, we can divide m plus n divided by 2 and we get one of those values, but we also want the other value, which is going to be one more than it. All right, so if we can solve this for a general k, then depending on whether we have an odd number of numbers or an even number of numbers, we can always substitute k is equal to this specific value and get the median. So any questions about this? So let me actually write down what we want to do. The overall problem is therefore to find the kth smallest element in two sorted arrays using binary search. On one of the arrays, and we are just picking one of them arbitrarily here, but you could pick the smaller one. Right, that's going to be our first array, the other array is going to be the second array. So I hope the task is clear. Yeah, Veera. Yeah, you can unmute yourself.
Sorry, Omkar, that was from the previous hand raise.
Oh, okay, okay.
Uh,
Yeah, Aditya.
Hey Omkar, one quick question on the problem statement. You defined it here.
Hmm.
What if k is greater than m? Then it will not need to be array of length m, right? You mean m plus n.
Yes. So two sorted arrays of combined length m plus n, right? Combined length m plus n. And we're going to do that by doing binary search. Binary search is done on a single array, so we're just picking one of them arbitrarily to do binary search on. So the assumption here is that the value of k is well defined, just like in the sorting class. You go back to that problem statement. The value of k was assumed to be well defined, which means we cannot throw up our hands and say we couldn't find that number. It must exist in the data set that's given to you.
Yeah.
So yeah.
So Omkar, the last line, right? Using binary search on the array of length m, or you mean m plus n here?
So there are two separate arrays. So that's what makes this tricky, right? If you had to use binary search, what would we do binary search on? We can't do binary search simultaneously on. I mean, or at least that would seem very complicated to do if we were to do binary search on two arrays somehow, in parallel. Maybe the we could think about that if this attempt does not work out. So let's start by trying to think in the way that we were thinking on a general binary search variant problem. And if it works, if it then it's good. If it doesn't work, then we can think about more complicated.
Sure, sure. But my
Yeah.
question is that let's suppose the first array length is 2 and
Hmm.
second array length is 5.
Hmm.
So you are saying that you will do the binary search on the array of length of 2.
Yeah.
But what if the kth element which you are trying to find out is 4?
Yeah. So we have to. So it may not be. We may not find it there.
Mhm.
And so let's think about what we will do if we don't find it there. You know, things may just emerge out. Once we start analyzing what to do, uh, we might just see what to do for all of these possibilities.
Sure, thank you.
Right? If it's there, then where is it there? Where is it present? And if it's not present, then when the search ends unsuccessfully, can we get the answer directly?
Got it. Yeah.
Right. So many of the binary search variant problems, if you remember, had this component that it was not guaranteed that we would find what we're looking for uh, in the array. But if we didn't find it, that itself would tell us something about the answer. So we'll see if uh, we can get something like that here. Veera, you had a question, or should I just lower your hand myself? I saw your hand raised, that's why I'm asking. Okay. Okay. So um, if you go back to the general template for binary search, you might remember that we have an array, and initially uh, our search space is the entire array, and we follow essentially a decrease and conquer approach where we decrease the problem size by a factor of 2 by checking the middle value at the middle index, and we figure out whether the key that we are searching for or the property that we are searching for is satisfied by that middle number or not. If it's not, then we should be able to instantly find out which direction that uh, key might lie in, on the left or the right side, and then so with a single comparison we can reduce the problem size by a factor of 2. So in general, if I am the root manager given responsibility for the whole array, I would my subordinate would get one half, roughly one half of the array. His or her subordinate would get half of that, and so we basically a chain of subordinates, each grappling with a problem of half the size. And so in log n steps, we would get down to the, to a subproblem size 1 or 0. So a general manager in this chain, an arbitrary manager in this chain, would be given a subarray that starts at not from 0 to n minus 1, but let's say from start to end. And so what would this general manager do? Well, find the middle index first of all. So the mid value would be the average of the start and end values. You can write it as start plus n minus start by 2 if you've seen the series. But if you have not, just take this to be the average of start and end. And then we compare if the key that we are searching for is equal to nums of mid, then we have found the answer. Otherwise, maybe the key that we are searching for is on the left side of the middle value, right? As I'm assuming this is a sorted array. So if it's on the left side, the way this manager will delegate the work to the subordinate is by reducing the end index to mid minus 1. Otherwise, the key is bigger than nums of mid, and so the way the subproblem would be reduced in the next step is to move start to mid plus 1. And this whole thing will be implemented in a top-down way from the root manager down to the leaf level. And so we are going to start out with the root manager who will see an initial value of start equal to 0 and an initial value of end equal to n minus 1. And we will keep executing this until the subproblem size has become 0 in the worst case. So when the subproblem is non-zero in size, start will be less than or equal to end. We have a well-defined sub-array to explore yet. But if the search ends unsuccessfully, then we know that at the end here, the value was not found. And we also saw the property that an unsuccessful search ends with the start index being one more than the end index. Right? Wherever the value was supposed to be found, if it's not found, the start index will be pointing to the value just after it. The end index will be pointing to the value just before it. So this is just to remind you of what the code for the template was for binary search. There were 3 regions. Some of the problems we had 2 regions, but in this case, we're going to assume that we are doing, we have these 3 regions. So when we do binary search, this time searching for the kth smallest element, we will do the same thing. We will pick a middle value, try to find out in constant time whether it is equal to the kth smallest element that we are looking for. If it's not, then try to figure out whether it lies on the left side or the right side, and then change the end and the start indices accordingly. And if things are not found, then we'll see what to do. So let me actually draw this out because a diagram would be very helpful for this problem. So I'm drawing the first array now as the top rectangle. The second array is bottom rectangle. This array is of length m. This array is of length n. Actually move this down. So assume that the 2 arrays could be of any relative size, right? I assume that we are doing binary search on the smaller array, but it's not necessary. even if m was bigger than n or if m was less than n, our code should be able to work. So we're going to do binary search on the first array. So the first array will have indices starting from 0 ending at m minus 1. The second array will have indices starting from 0 ending at n minus 1. And so when we do binary search on the first array, we are going to compute a middle index, and then we want to be able to check whether that middle index is equal to the value that we were looking for. So going back to this same structure, we'll try to do the same thing. So let's say we initialize start to as 0 and end as m minus 1. While start is less than or equal to end, we will compute the mid value as the average of start and end. Now, what we want ideally, let's see if we can get that. What we want ideally is, I'm just going to write this in English first, or let's say in comments first. If this value, if nums1 of mid is the kth smallest element, then we want to, declare that we have found it. Now, how do we write this in a programmatic way? How do we translate this English sentence into an actual condition? How do we know that this value is the kth smallest element? So if it is the kth smallest element, then what's going to happen is that so what does it mean for this mid value to be the kth smallest element? It means that there are a bunch of values to the left which are smaller than it, and there are a bunch of values potentially in the other array that are also smaller than it. But we know that if we had to merge these two sorted lists together, as in the brute force approach, this value, this mid value, would be the kth value, exactly the kth value in that merged version of the two sorted arrays. That means the number of values in these two orange regions combined must be equal to k minus 1. Right? That's the condition for this mid value to be the kth smallest element combined overall. Everything to its left is smaller than it, or less than or equal to than it. And we don't know what this region is, but there might be some region in the second array which also consists of elements that are less than or equal to this value. Now, can we identify how long this region should be? Well, if this is the mid index, I know what the mid index is. That means from 0 to mid minus 1, I have a bunch of numbers here. In fact, I know exactly how many numbers there must be here, because from 0 to mid minus 1, there would be exactly mid number of numbers. Right? If mid is equal to 5, for example, then from 0 to index 4, I know that there must be 5 numbers. And what I'm saying is that the total number of numbers across the two arrays in the orange region must be equal to exactly k minus 1. So if the yellow rectangle here has mid values, then this rectangle here must have k minus 1 minus mid number of values. Right? So I'm just unpacking what does it mean, or what does this being the middle element, what does this being the kth smallest element imply? It implies that whatever be the number of values here, we know it's going to be equal to mid, when combined with these values, they would all be less than or equal to the kth smallest element, and they must be exactly k minus 1 in number. If it makes things easier, try to assume all the numbers are distinct, although it doesn't make any difference. This should work even if there are duplicates. But to help you understand, or to help yourself understand this for the first time, just pretend that all the numbers are distinct. It would make it a little easier. Now, if these values are all less than or equal to mid, and mid is going to then appear after them in the merged output, that means all of these other values, which I'm painting in green, they are going to appear after this middle value in the merged output or in the sorted output. So we have to somehow convert nums of 1 mid is the kth smallest element into a condition here. So if all of these orange values are less than or equal to mid, it definitely means that this value must be less than or equal to mid. This value should be less than or equal to mid, which we know must be the case since the array is already sorted. And this green value must be larger than the mid value, which is also guaranteed. But what is not guaranteed to us is that these two values in the second array are less than or equal to that mid value and greater than or equal to that mid value respectively. Right. So if mid is really the kth smallest element, it means that all of these orange values must be less than or equal to it, which will be true if this last orange value is less than or equal to it. Because if this last orange value is less than or equal to it, then obviously everything else will be less than or equal to it. And likewise, if the first green value is more than or equal to it, then obviously all these other values will be more than equal to it. These values are already guaranteed to be more than or equal to it. These values are already guaranteed to be less than or equal to it. So the condition that we have to check is whether this value is less than or equal to it and whether this value is more than or equal to it, or in other words, whether this mid value lies in between these two values in terms of the magnitude. So the index of this element is going to be k minus 1 minus mid minus 1, right? Because if there are n values here, the last index would be n minus 1. So if there are these many values here, I just take that, whatever that expression is, and subtract 1. That gives me the index here, and the index here is going to be k minus 1 minus mid, 1 more than it. So I'll go back now and translate this as, if my mid value is the kth smallest element, that means if it lies between these two values, so nums2 of what is the index of that orange, the last rightmost orange number, k minus 1 minus mid minus 1. I could write this in a simpler way, but I'm just going to write the raw expression just so that you see where it's coming from. So this has to be less than or equal to nums1 of mid, and in turn that value needs to be sandwiched on the other side under it should be less than or equal to this value, which is nums2 of k minus 1 minus mid. So if this is the case, then we have found the kth smallest element, right? So if the problem asks us to return the kth smallest element, then we could do that by just returning the mid value here. nums1 of mid. Right, we'll change this later for the specific problem we are looking at, but conceptually that's we can declare that we have found the result. Any questions about this part? Yeah, Dinesh?
Yeah, I'm kind of having hard time connecting k and mid value. So we if we know like 10th large smallest value, then what is the relation between mid and k? Or we are using mid to just find the number, so we know the value of kth.
Yeah. So the question is, if we were to find the 10th smallest value, I'm trying to just search for it by doing binary search on one of the arrays. Right, I started from the mid value, the
But
mid
how do
index
we
here.
know 10th smallest value?
Yeah, so how do we know that this is the 10th smallest value? Well, if this is the 10th smallest value, and if I see that there are, for it to be the 10th smallest value, if I see that on my left there are 4 values, right,
Yeah.
then it must be the case that there should be 5 values in the second array, which should also be all smaller than my value. And once I cross that, everything else beyond that must be bigger than my value.
Okay. So to find out the 10th smallest value, we have to find combined 10 elements before the mid.
Yeah, so imagine if that brute force approach where we were merging these values one by one. We
Yeah.
are saying what must be true if this is going to be the 10th value that will get inserted in the merged output, right?
Before
All of
the,
these values must have been inserted before it.
yeah, yeah.
Now, if I check how many they were, if my mid index was let's say 7, then I know there must be 7 values before me just from this array.
Yeah.
So that means there must be 2 other values from the second array, which must have also gone before it, but no more than 2, exactly 2 values.
Okay.
So that means if I look at the second value here, I have to I'll need to verify that it is indeed smaller than it, but the third value is not. The third value should be bigger than it. Then only this will go first.
Our search is not based on the value, but on the index.
Yeah, binary search happens on based on the index. We just randomly pick the middle index and check.
See,
Yeah.
so we are not looking for the target, but we are looking for the target index.
We are looking for the kth smallest element, and we are trying to see what must be true if I pick the middle number and by some miracle it happened to be the kth smallest element. How would I know that it's the kth smallest element? I would know if I could check this condition. If it is the kth smallest element, then these many values must have gone before it, and from the other array I should have k minus 1 minus mid value that must be smaller than it, so they must have gone into the merged output before it, and no more than it. So the very next value, I need to make sure that it is bigger than the value that I am focused on.
So the mid for nums1 and mid for nums2 will be different, right?
Yeah, we are not doing mid on nums2 at all. We are just doing binary search on the first array.
Oh, okay.
So that is the, I would say, an important point. Right, there are 2 sorted arrays, but our binary search template is being used on one of those arrays. You can pick which one you want. I picked the first one arbitrarily. You can pick the smaller one if you like. But this is the condition here for this value to be the kth smallest element. Manish?
Hi, Omkar, I'm not able to get my head around taking the smallest array. Let's take an example of m and n being like 10 and 2, right? And in that case, 12 will be the total size. And and if I start going on the smaller array, the kth element, it would be 6. So and that only has two elements. Like, so how will that, like, I'm not able to get that. And second one,
Okay, okay, well, hold on. Let me just draw it. So you're saying M has a length of 10
yeah,
and N has a length of 2.
two, yeah.
So
Okay.
K is bigger than the
What is the value of K you're picking?
So K we said like 10 plus 2 by 2, right? 6.
No. Okay, for the median problem,
Yeah,
10, yeah, K would be 6.
yeah. And
So,
yeah.
so we would pick, so we would, let's say, which array do you want to do binary search on?
The N.
The N array, okay. You want to do binary search on this. So, uh, you will have start equal to 0, end as 1. So when you pick the mid index, it's going to be 0. 0 plus 1 by 2 is 0.
Yeah.
So this will be your mid value. Now, the question is, when will this be the sixth value, the sixth smallest value? This will be the sixth smallest value uh, if zero values here. So there'll be zero values here before it. We know that.
Yeah.
And there must be therefore 5 other values in the first array. There should be 5 other values in the first array that should all be less than my value.
When you say my value means nums to 0
Nums
index.
2 of yeah. So let me paint this as white. This is the value I'm focused on. Is this the sixth smallest element? Am I lucky? That's my question. Well, I'll be lucky if I see that all the values on my left combined with the appropriate values at the beginning of the second array make up 5 elements,
Mhm.
and everything beyond that, both in my array and in the other array, make up values that are bigger than my value.
Mhm.
Right? Then I can say that this white value is indeed the sixth smallest value. So if I look at index 4 in the other array and I see that this value is smaller than my value, and if I look at index 5 in the other array and I see that that value is bigger than my white value, then I know I'm lucky. That means I know there are 5 values in the other array which are smaller than me. I know there are 0 values in my own array which are smaller than me. That means I am guaranteed to be the sixth smallest value because everything else after that is bigger than my value.
Hi, Omkar.
Yeah.
Why you have to check the green portion if you already compared like
No,
0 to 4?
because if this green value was smaller than my value, then it would go into the merged output before me, right? So then I would not be the sixth smallest. I would be the seventh, eighth, ninth,
Got it.
like
Yep.
that.
Yep. Yep.
I need to ensure that there should be exactly 5 values in both the arrays that are smaller than me. Then
Yeah.
only I can claim to be the sixth smallest value.
Correct. Yes. That's true.
So if I check how many values there are on my left in my own array, uh, I know then how many remaining values there need to be in the other array that must be smaller than me. And everything else, both in my array and in that other array, must be bigger than me. So instead of checking all values, it suffices to check the largest of these values and check that it's smaller than me, and to check the smallest of these values and check that it's larger than me.
Okay. And
Right.
if I'm not lucky and the index of num2 is not the sixth largest, like smallest value, then
Yeah. So then we have to look at the other two cases. So case one is the lucky case where the kth smallest element happens to exactly be the value at the middle index. Now, what if it's not? If it's not, then there are two options, two possibilities. One possibility is that the kth smallest element overall lies somewhere on the left. So let's look at that. I'm painting it blue just to show that it lies somewhere to the left. That's the true kth smallest element. So I'm going to write it first in English. Else, if the kth smallest element lies in the left zone. The left zone is the zone that is, to the left of the mid index from 0 to mid minus 1, the orange zone, right? The green zone is the right zone. So if the kth smallest element lies in the, if I can somehow figure out a condition for it to lie in the left zone, right? If I detect that it lies in the left zone, then I know that the right zone can be completely dropped from my search. So I can then reduce my end value, my end index to mid minus 1. That will allow me to decrease the problem size by a factor of 2. So, but I'll write that later. What I need here, or let me just write it here. If I can somehow detect this, then I'm going to do end is equal to mid minus 1. The question is, what is that programmatic condition that guarantees that the kth smallest element lies in the left zone? So let's look at that same picture here. For this blue, so if this blue value is the kth smallest value, I thought I was checking that, you know, whether my value is the kth smallest value, and I painted these regions according to that. But if this blue value happens to be the kth smallest value, then my diagram will need to be modified, right? In particular, if I look at the second array, if my true orange region is actually smaller here, right? If the blue value is the true kth smallest element, then there are fewer values in the first array that are smaller than it. That means there must be more values in the second array that are smaller than it. And that means there must be more values in the second array that are smaller than my value. Right? So hello, can you hear me?
Yeah.
Okay.
Yeah.
So
Omkar,
yeah.
so just to understand the problem, so if the blue region, then k minus 1 minus mid, that would be also less than the mid. Then we can say that probably that this is in the left zone.
Yeah, so if the true value is this blue value, that means I'm going to see a bunch of values here which are also going to be orange in color. Right? I thought they would be, I was hoping they would be green from this index onwards, but actually I was wrong in my estimate. The true value, the true kth smallest value actually lies here, which means this orange zone in reality should be longer, which means this value, which I thought would be bigger than my value, will actually be smaller than my value.
But why, like, the orange section will be greater? Like, why it will increase? Like, I didn't get that.
So I thought that my value would be the 10th smallest value. So I made these regions assuming that there will be 9 values combined, which will be smaller than mine.
Okay, combined.
Right?
Okay, yeah.
Yeah. But unfortunately, it turns out that in reality, this is the 10th smallest element.
Mhm.
If this is the 10th smallest element, now there are only maybe 1 or 2 elements here which lie to its left. That means there should be more elements from here which are going to be smaller than
Got it.
the 10th smallest element. That means there'll be more elements here which will be smaller than my own value.
Got it.
So in particular, so if you look at this check that we made, that whether my value is sandwiched between that orange and that green value, this condition is going to be violated in one particular way, right? This latter condition is what will be violated if the kth smallest element lies to my left, because this value is going to continue to be smaller than my value. We are saying that there'll be a bunch of more values that will need to be orange in color, and so this condition will get inverted, right? So if this is not true, there are two ways in which this cannot be true. Either this value is bigger than this value, sorry, smaller than. Either this value is smaller than this value, or this value becomes bigger than this value, right? Now, it turns out that the first of those violations is what will happen if my kth smallest value lies on the left. My kth smallest value lies on the left. That means this value, which I was assuming to be green, is
Mhm.
actually going to end up being orange.
Yeah,
Right? It must be orange.
yeah.
And so if so, in other words, if I check that nums2 of k minus 1 minus mid is actually uh, instead of being greater than or equal to my value, ends up being less than my value, that means the kth smallest value must lie somewhere to my left. Let me write this down and then I can take more questions. Else, if this value nums2 of k minus 1 minus mid, which visually is equal to this green value we are looking at in this diagram, if this value happens to be smaller than my value instead of being bigger, greater than or equal to, then the kth smallest element must lie somewhere to my left, to the left of my value. Um, and so I would move end to mid minus 1. And you can now guess what we'll do with the third condition. Else,
A is on the right hand side.
yeah. So if the kth smallest, I mean in English, the third condition is that the kth smallest element. So it's not my value. The question is, which direction do I expect it to lie, on my left or on my right? The third condition is I find that if it's present, it needs to be present on my right side. And the programmatic condition, which will automatically be true if the first two are not satisfied, is, so let's see first visually what do we expect. If the kth smallest element in reality is this blue number uh, lying here, so I was wrong in my assumption that my number is the kth smallest. It turns out that this blue number is the kth smallest. That means I'm going to scoop up more values from the first array within the orange zone. Right? There are more values in the first array that are going to be in the orange zone. So there'll be fewer values in the second array, which will be in the orange zone. The orange zone basically means the set of values that are smaller than the kth smallest element. So that if there are a set of, if there are fewer values here that are smaller than it, that means this value, I can definitely say that this value, this orange value, must be smaller than so sorry, not smaller than, this value must be bigger than this value, right? Because if this orange region is going to be shorter here, that means this, the color of this number must have become green. And if it's become green, that means it must be bigger than the kth smallest element value, which means it must be bigger than my value as well. Right? This is what I'm observing. And so the condition here is that this value, which I thought to be orange, is actually green. The second condition was, I thought this value is green, but it ends up being orange. In the third case, what we're talking about is I am expecting this value to be orange if I was lucky, but it's actually green. That means the orange region here is shorter. That means here it must be longer. The kth smallest element must be uh, present on my right side. So the violation here is that this particular inequality, this particular condition is being violated here. So that means this value, which I thought to be orange, nums2 of k minus 1 minus mid minus 1 is actually bigger than my value. Now the thing is, this code is itself just following from the diagram. If you remember if you've seen my trees class, those problems where we have the in order and the pre-order traversal given for a tree, and then we have to reconstruct the tree. You might remember there also that the code looks complicated. It's really it just follows from the diagram. So don't look at the code and try to understand the code directly here. Try to understand the diagram. The code will just follow from the diagram. So if this other condition is violated, right, that means this value is actually bigger than this value. That means I thought this value would be less than or equal to it. It ends up being bigger. That means this green region is actually bigger. It means the orange region here is actually shorter. If it's actually shorter, then the corresponding orange region here must be longer before we reach the kth smallest element. So the kth smallest element must lie on the right side. It's not going to be the value that I am at. So in that case, what I need to do is to ignore the numbers on my left, because I know the kth smallest element does not lie on my left. I can change start to mid plus 1.
Thank you, Omkar. I think I got confused when you said like you're just going over one array. In fact, like you are going over both arrays in this case.
Yeah, so if I look at the condition for my number being the kth smallest, that automatically puts a condition on what the second array should look like, or up to what point in the second array I should go to gather up the numbers that are smaller than me, and what is the range of indices here which are going to have numbers that are bigger than me.
Right.
Just because when I pick a particular index here, that automatically tells me how many numbers there are here that are smaller than me, how many numbers there are that are bigger than me. So if I define my rank, if I'm looking for the kth smallest, that automatically tells me for my number to be the kth smallest, how many numbers in the other array there should there be which are smaller and larger than my number. So this is going to be so if the kth smallest element is actually found in the second array, sorry, the first array, which is what we are doing a binary search on, we are guaranteed that at some point we are going to hit this first condition and exit. But what if it's not found in the first array? Maybe it's not there. In that case, this while loop is going to exit with the same condition, start being equal to n plus 1. Start is equal to n plus 1, or if we come here, I should say, that means the kth smallest element is not found in the first array. So it must be in the second array. Now, can we instantly tell where it must be in the second array? So let's draw a diagram for that. I'm going to redraw this nums1 and nums2, and we are now looking at a diagram where binary search ends unsuccessfully. If it ends unsuccessfully, it must have ended somewhere in the first array where the start index was pointing here, the end index is pointing here, right, where start being equal to end plus 1. And what do we know? We know that all the values before, so this is the boundary. This is the boundary. Everything to the left of the boundary is in the left zone. That means all of these numbers were numbers that were that turned out to be smaller than the kth smallest element. all of the numbers that are in the right zone ended up being bigger than the true value of the kth smallest element, which is why whenever we were in the right zone, we kept shrinking, we kept jumping left from there. Whenever we found our index to our mid index to be here, we kept incrementing the start index here. Eventually, we shrunk down the problem size to 0, and so this is the boundary condition, which if you've gone through the binary search variant videos earlier, you would remember that this looks familiar. Now, at this point, I know the kth smallest value lies somewhere here. I don't know where it is. I want to figure out if I can tell instantly where it is. I know that all of these values are smaller than the kth smallest element. How many such values are these? Well, the start index tells me that, or the end index tells me that. There are exactly start number of values which are in the orange zone. Now, if I know that in the first array there are exactly start number of elements which are smaller than the kth smallest element, then I know that in the other array there must be exactly k minus 1 minus start values that are smaller than the kth smallest element, which means I know the index at which the kth smallest element must lie in the other array. It's going to be index k minus 1 minus start. Right? Because these indices are from 0 to k minus 1 minus start minus 1. So this will be at index k minus 1 minus start. So that means I can declare here that I know where the kth smallest element is. I can just return that corresponding value from the nums array at this blue index k minus 1 minus start. And so if the problem statement was pristine and without complications of the kind that LeetCode adds on top of this, this would be the short and sweet piece of code that would find and return the kth smallest element in both arrays. So everything else is just going to be what LeetCode wants, right? Because they ask us to find a median, so now we have to worry about whether the combined length is even or odd, and if so, find the two separate numbers, the kth smallest and the k plus first smallest, if turns out that the combined length is even. Otherwise, we would just return this value. And there are there's one other complication that that we need to look at, but conceptually this is the algorithm, and it can be solved using the same template. So let's see if there are questions about this. So this is unsuccessful. It ends unsuccessfully. Manish?
Sorry, I forgot to lower my hand.
Okay.
Hey Omkar, just a quick question. The second part does make sense, but let's say whatever we did, we did a binary search on nums1 and we took nums2 as the second candidate. Let's say we reverse the process and we do it again, then also we get the answer, right? If it was not,
Yes.
it was not
Yeah. Yeah. So if it's not there in the first array, you could exactly run this on the second array, and that now you will be guaranteed to find it in the second array.
Cool.
So it is better to start with the bigger array than the smaller because there is more possibility to be there.
Yeah, I mean by default, yes. Um, you can say though that the bigger array is going to take a little longer time because log of, in the worst case, log of m or whatever, log
Mm.
of the length of the bigger array is going to be more than the log of the length of the smaller array. But I don't think they care about that here because they just said find find just do this in logarithmic time, right? It doesn't matter whether it's in log m or log n.
That means binary search, right?
Yeah, so that's the hint, I would say, towards doing binary search. So we'll look at the complications, but any questions about this pristine version of the solution before we look at the other complications? Vineet?
Yeah, I was just thinking like if you were to do two binary search, then the complexity will become log of n into m. It won't be log of n plus m, right?
Yeah, yeah,
Okay,
yeah. It's going to be log of m plus log of n, which is log of m times n. Yeah,
okay, thanks.
yeah. Veera?
Would you please explain about the last line in this code when we find it in the num? Yeah, that's one.
So uh, when binary search ends unsuccessfully on the first array, right? So in each step, what binary search is doing is either it's finding the kth smallest element in the first array, or it turns out that my mid value lies, falls into the left zone. I mean, just describing this in a slightly different way. If my mid value happened to um, fall into the left zone here, which means my kth smallest element actually ended up being to the right of the mid value. So it's actually this case that I'm talking about. Then I would be uh, cutting out everything on my left, right? Because I know the value is guaranteed to be on the right side. And likewise, if my mid value falls into the right zone, uh, which means that the kth smallest value actually lies on my left side, which is actually what I've shown here. Then I can cut out the right side. So we are guaranteed to cut out. We are guaranteed to either move start to mid plus one or end to mid minus one, which means the problem size is guaranteed to reduce. But in the worst case, what will happen is we'll end up with a problem size 1, and even that number is not going to be the right number, right? So maybe at some point start and mid both end up pointing to the same index. So mid naturally will be their average and will also be the same index, right? Mid is equal to start is equal to end. That's what will happen when we have a subproblem of size 1. Now at that point also we might see that this is not really matching the condition that we were expecting here. At one of these conditions is violated. Question is which one is violated. Um, both of these can't be violated, by the way, at the same time, because you can't have this value being bigger than nums of mid and this value being smaller, because then that would make this value bigger than this value, which contradicts the fact that the second array is sorted, right? You can never have a condition where this value is bigger than this value. It's guaranteed that this value is smaller than this value. And like I said, assume there are no duplicates if you want to avoid cluttering your thinking at the beginning. So uh, going back to this, either start will be then moved to either start will be moved to mid plus 1 or end will be moved to mid minus 1 at this point. right? So either we'll end up with start being here and end being here, or we will end up doing end is equal to mid minus 1, which means either we will, sorry, end is equal to, yeah, end is equal to mid minus 1, which means end will be here and start will remain wherever it is. In either case, start and end are at consecutive indices, start being n plus 1, and depending on which of these two conditions it was, this value, so actually let's go back to the code. If end was mid minus 1, that means the kth smallest element lies in the left zone, right, or somewhere on the left, somewhere to my left. That's when we do end is equal to mid minus 1. So this green thing is what we do if the kth smallest element lies on the left of my index. That means this value, what I thought was the right white value, is actually going to be green. And so this boundary is going to mark the boundary between the green and the orange region. Conversely, if it had so happened that start had ended here and end would have ended here, then that means this value, which I thought was green, is actually orange. That's why it went in the other case, which means uh, this would be the boundary between the orange and the green regions. Everything up to here would be orange and everything to the right would be green. So wherever start and end up, the boundary between them is what separates the orange region from the green region. Orange region consisting of all the numbers that are guaranteed to be smaller than the kth smallest element. All of these numbers that are guaranteed to be bigger than the kth smallest element. Now, if that is the case, then now we ask, where is the kth smallest element? It must lie in the other array. Question is, where in the other array, at what index does it lie? So if we know exactly how many values here are smaller than the kth smallest element, that's equal to start. We know that there must be k minus 1 minus start values in the other array that are smaller than the kth smallest element. And then the kth smallest element must appear right after it in the other array. So we know what the index of the kth smallest element is, which we can return instantly if the search ends unsuccessfully like this. Does that clarify?
Yeah, thank you.
So, so this is what we have right now, and now let's start looking at the complication of this problem being a median finding problem. That means we're not just required to return one value, kth smallest, or if it was the kth largest, we would just do the same thing. Like the first largest element is also the nth smallest element. So the kth largest element would also be the n plus 1 minus kth smallest element, something like that. So same piece of code would run, you just need to work with a different value of k. But for median, we have this complication that what we did works well with m plus n being odd. Works well with odd number of elements, whatever we have written so far. But with even elements, we also need to find one more value. Right, going back to what we had at the beginning. If m plus n is odd, we could set k to be this and find that value and return it. If m plus n is even, we could set k to one of these values. Let's say we set it to this value. We could find it, but then we also need to find the k plus first value so that we could take their average. So we need to find the successor. So the k plus first smallest element would be the successor of the kth smallest element. So need to find the k plus first smallest element as well. Now you can think of finding it by doing the same thing that we did, find the kth smallest element. That would be like a bit of an overkill because you've already done the work to find where the kth smallest element lies, right? You already have, uh, either a successful search where you ended up with a white number as the kth smallest value, or you ended up with an unsuccessful search where you have a blue value as the kth smallest value. And you have this painted region that you know the boundaries for. So we just need to find the successor and then take the average. So let's look at both cases. If the kth smallest value ended up from the first array, then we would have found it somewhere, right, for some value of mid. What would be the k plus first smallest element? What would be the successor of this? We know all the orange values are smaller than it. There are two values that we know are bigger than it. Well, everything in the green region in both arrays is bigger than it. But the immediate successor of this white value could be either this green value or this green value.
And anything could be there, whichever is a smaller out of those two green.
Yeah, so we just pick whichever is the smaller out of these two as the successor. Do we know the index of this? Yes, it's mid plus 1. Do we know the index of this? Yes, it's k minus 1 minus mid. I don't have to think. If I have the diagram with the labels, I don't have to think about what k minus 1 minus mid means and all those things. It's already just whatever is in the label, I just blindly copy it. So what I'm going to do is, instead of returning this, I'm going to say, I'm going to have a variable saying this is the kth smallest value. Kth smallest is nums1 of mid. And I'm going to also identify what its successor is. The successor is going to be the smaller of two values. One of them is nums1 of mid plus 1. And the second value is nums2 of k minus 1 minus mid. Nums2 of...
One thing you would have to check, Omkar, that you could have go out of the boundary with mid.
Yeah, so that's the second complication, which I'll come to after writing this one at a time. So nums2 of k minus 1 minus mid. So I have both the kth smallest value finalized, but now I also know how to finalize the value of the successor, the k plus first smallest element. Same thing here. Suppose I were to write the kth smallest value. Instead of returning it, I'm just going to replace it with a line that says the kth smallest value is nums2 of k minus 1 minus start. The question is, can I find the k plus first smallest element? So let's go back to this diagram where the kth smallest element was found in the second array because the binary search in the first array ended unsuccessfully. So the successor of this could either come from the second array, in which case it would be this value, or it could come from the first array, in which case it would be the value at the start index. Right? The two smallest green values are the two candidates for being the successor. So that means nums1 of start and nums2 of k minus start. This index is k minus start. These are the two candidates. So we'll pick the min of nums1 of start and nums2 of k minus start. So that guarantees that we have both the kth smallest and the k plus first smallest elements, and then we may or may not use the successor value. If m plus n is odd, so if m plus n is odd, then what we return will just be the the single value, right? K is the kth smallest value. Otherwise, if m plus n is even, then we will return the average of the two values, kth smallest value and the successor. Just making sure the average could be a decimal number. It need not be a whole number, as you saw here. 2.5 would be the output. So this is what we would return, and of course we do need to set this in code itself right at the beginning. So assuming that we know that m is the length of the first array, n is the length of the second array if it's not explicitly given to us. If m plus n is odd, then we will set k to this value, m plus n by 2 plus 1. Otherwise, if m plus n is even, we will be trying to find the kth smallest element where k is m plus n by 2. So that's how we handle the complication of this being a median finding problem, in which case we might need two consecutive values instead of one. So this was the first complication. Now somebody did point out that in the process of doing this, some of the indices may not be valid. Why could that happen? Suppose, for example, that the first array had only one element, and the second array had more elements. Suppose m was 1. And let's say m and m, let's say m plus n was even. which means we want not just the kth smallest value. So let's say m is equal to 1, and um, this is the kth smallest value. So we've discovered this while doing binary search on the first array. We instantly find that it is the kth smallest value. If we had to find the successor, the code for finding the successor looks at this diagram, right, where it tries to find the min of this value and this value. Now, what if this value, what if this mid had ended up being the last element of its array? Then there would be no index beyond it, so mid plus 1 would not be a valid index. So that's one example where we could end up with an invalid index. So we can say successor index would be invalid. Another way in which we could get into trouble is, suppose the second array had only one element, right? And suppose in the first array this is where mid is at some point, and we find that we are in one of those cases where this value is not the kth smallest value, but the kth smallest value lies somewhere to the right of the mid value. Right? We don't know where, but let's say it lies somewhere to the right. So that means our orange, so we thought the orange region was this long, but our conditions, when we get into one of those three cases, we realize that our orange region is actually going to be even longer than what we thought. That means in the other array, it would be even shorter than what we thought. Right, going back to this diagram, if the orange region is bigger than what we thought, then in the other side, it could be shorter than what we thought. So it's possible that when we look for k minus 1 minus mid minus 1, we could end up with an index that's less than 0. Right? How could that happen? Because imagine there's only one valid index here, there's only one element here, and at some point we are at mid here, and let's say this orange boundary is exactly that single number. Right? It's exactly that single number. Now we land up in a case where we realize that the median actually lies on the right side here. So we are going to, in the next step, we are going to increase the value of mid. So start will become mid plus 1, then when we recompute mid, it's going to become bigger. When it becomes bigger, this is going to become smaller in the next step. K obviously remains fixed, but when mid becomes bigger, this will become smaller. So if it was already at that lone single index 0, this could become negative. And if you don't see this right away, just try it with some test cases. You'll see, where they fail. And this is another way in which you could end up with an invalid index on the left side. So when mid moves to the right in the next iteration, what was this value? It was index k minus 1 minus mid, because we will be looking up the values at these two indices, right, in each step. So k minus 1 minus mid minus 1, k minus 1 minus mid minus 1 could become less than 0. In other words, it may not exist. The point is, we could exceed the index on either side, trying to look for a value that does not exist because we cross the right boundary or cross the left boundary of either of the two arrays. So how do we deal with this? I think the simplest way to deal with this is to imagine that there is minus infinity to the left of, once we cross the left boundary, we see minus infinity, and once we cross the right boundary, we see plus infinity. Because if we are trying to find the successor of this value, and let's say the successor does not exist here because there is no element after this, by making it infinity, we are guaranteed to pick the other value. And likewise, if we are trying to search for this value, and we are trying to and we find that there is actually no value that's in the orange region here, then when we compare this with mid, we are guaranteed, if we put a minus infinity here, we're guaranteed that it's going to be less than mid. So instead of getting into an error, that condition will be true by default. We actually don't even need to check that condition, but we, instead of making the code more complicated by adding an edge case to see whether or not this index exists, if we just treat it as minus infinity, then we know we are not getting into trouble here. We know that this orange value is not exceeding the mid value here. So if you understand this code, then what I would suggest, or at least what I did, is just add a function. So whenever you're looking up an array index anywhere in your code, now some of these will result in could result in an invalid access. Some of these may not, but you won't have time to think about which one will and which one may not. So just replace all of these lookups with a function that takes the array name and the index, and it returns the value as long as the index is valid. Otherwise, it returns a minus infinity if the index falls less than 0, and plus infinity if it falls beyond m-1 or n-1. So what I mean is, I could define, let me do it here only. I could define a function called get, which takes an array A, an index I, and if the index is invalid in either direction, if it's less than 0, we return a minus infinity. If it's more than or equal to the length of the array, that means it's crossed the right side, we assume it'll return a plus infinity. And if neither happens, then we know the index is valid. So we can do the lookup. So this then would get replaced with get nums2 k-1 minus mid, which is easy to do if you're typing this up, right? All you have to do is to add a comma here and a get here. Just add a comma between this and delete this bracket and you put it as get. Some of these won't overflow. I mean, some of these won't overflow or underflow. Like, for example, when you're doing binary search, you're going to be doing binary search on valid indices. But if you don't have, time to think, just do it for everything and it should work. Obviously, this will always work because we know the kth smallest value must always be found no matter where we are. But this may or may not work. So you could add a get here. And there could be other ways of doing this. Umesh?
Yeah, I was asking the same question. Like the second case that you explained, that may not occur when we are doing binary search with the smaller array, right?
Yeah,
So
yeah.
this index out of range might happen while checking for the successor.
Index out of range might happen when checking for the successor. Yeah. But there could be issues even with the same array. So let me take one more example here. Suppose suppose both arrays were actually of the same size, 1, 2, and let's say 3, 4. And suppose we want to find the second. Suppose we want to find the median here, for which let's say we have to find the second smallest element first, right? Now suppose I decide to do a binary search on the first array. I'm going to start out with this being mid, right? So if this is mid, that means mid is 0. What is the guarantee that, how do I know if this is the second smallest element? Well, if this is the second smallest element, what should happen is there should be exactly one element that is smaller than me in both the arrays. Now there is nothing to my left which is smaller than me. So that means this value, this value in the second array needs to be orange. It needs to be smaller than me. It turns out it's not. Right? So the condition that we check is this should be smaller than me and this should be bigger than me. Now 4 is indeed bigger than 1, but this condition is violated at the first check that going back to that code. Which case are we in? Case 2 or case 3 here?
Case 3.
Case 3. Yeah, so this value is actually bigger than mid. So we are going to change start to mid plus 1. So so this was mid, and in the next step start will become mid plus 1, and end is obviously already here. So that means in the next step mid will shift here. Oops. Mid will shift here.
But before that, we'll get out of the while loop, right?
No, only when start becomes greater than end. Only when the search space shrinks to nothing.
Okay.
So right now the search space was of size 2. After one iteration, now it's become size 1. So this is the lone element we are looking at. So the mid value, so the mid index is this. So now we are going to check, what is the guarantee that this is the second smallest element? Well, there is nothing here. Sorry, there is one element here. I know that this element is definitely orange. Let me redraw this because I don't have colors at this point. This is a new iteration. So I already see one element smaller than me. That means there should be no element from the second array that I need to consider. But my code, because it's short, it is considering it. It's going to try to access nums2 of k minus 1 minus mid minus 1. So k is 2, mid is 1, and so if you do 2 minus 1 minus 1 minus 1, we'll try to access an index smaller than 0 in the second array. So that's why rather than trying to think too much about whether it will happen for bigger or smaller, or I mean, I did spend a little bit of time on this, but it's just safer to just get the code running by just doing it everywhere, so that you're guaranteed that you won't wherever the element does not exist, you're going to get a minus infinity or a plus infinity value, depending on whether it's on the left extreme or right extreme. So that way, your conceptual code is not affected by it, by all those edge cases.
Okay, so that means for finding kth element in two sorted arrays, there also we need that check, right?
Kth element in two sorted arrays.
Uh,
You mean if this was not the median problem, but just the kth
yes.
smallest? Yeah. This will be required. So this code is actually something we wrote for kth smallest element. Yeah, this complication had nothing to do with the fact that we have to find the median. It's just that some of these indices may not be valid
Yeah.
when we are
Okay.
doing binary search, because we are looking into the second array, right? When we are doing binary search, we are looking for two values wherever we are in the first array. We guaranteed that in the first array we'll be at a valid index, because our code for binary search will always uh, create valid values for mid. But in the second array, we are looking at two numbers, an orange number and a green number, and then checking their ordering relative to my number. So that's where the problem could arise, because either of those two numbers might not correspond to valid indices, either because the array is too small, or it could be because we are at the left extreme there and the orange part does not exist, or we are at the right extreme and the green part does not exist.
Okay. Okay.
So because this is the standard template, this is going to run in log of m time or log of n time. I assumed m is the length of the array here. So the time complexity is order log m here, and it's a single binary search phase. So we're not doing multiple, we're just doing a single phase. And at the end, we're guaranteed to find and return the result. So let me just verify that I haven't forgotten anything here. This part, this is the core piece of code, and yeah, in the code I have, I have written get everywhere blindly, even though it may not be required in a bunch of places. But yes, I think this should work.
What will happen if we use heap instead of binary search? This index complications will go away, right?
If you use heaps, but you will end up using auxiliary space first of all, which was not used here. And the other thing is, you will still end up. So what will you do with the heap? You will like, how will a heap help you over the brute force?
Just to get kth elements.
Yeah, but just to get kth elements, if you would insert k of them, or what would you do?
Yeah, means yeah, we'll have to decide then which element we have to pick from which array, right?
Yeah.
It's
So it's
like,
not. It's so if k is relatively small, you might decide. Okay, like we looked at the brute force. We thought maybe we could just do this merge phase for the first k values.
yeah, so that we could do in heap maybe.
But then that will take order k time,
Yeah,
right?
yeah.
Order k. Now you could ask, well, order k, and here we have log m, which is better. The thing is, if k is relatively small, you're also guaranteed that um, the indices that you have. Suppose m and n are relatively large and k is small. Let's say k is, I don't know, 10 or something, and m and n are quite large. I'm guaranteed that the 10th largest element, or sorry, 10th smallest element is going to either lie in the first 10 spots here or the first 10 spots here. Right, so I can actually start out with my search space restricted even to 0 to 9 in both arrays. I mean, I can treat both arrays as being as small as that, because I know that this part, these two parts of the arrays are actually irrelevant. They need not even exist for me. So I can set end to be k minus 1 instead of m minus 1 if k is smaller than m, or if and if you're doing binary search on that. It's a small hack, but it's not going to make much difference. My point is, if you do that, this is going to take log k time. This binary search procedure will take log k time, because your initial search range is at most k. It can't exceed k anyway, you know that. So your heap or whatever other procedure you have will not be able to beat log k, which is what we get with binary search.
Yeah. And then the issue is which one you pick up from which array, how many elements you pick up from which array. That is also a problem.
Yeah. Yeah, if you have to pick up k of them from both, then I mean, it will already be proportional to k, then the complexity. So the point is, we don't even want to look at all the numbers, right? They're already sorted. So to do this in logarithmic time, and log k in particular, you have to find a way to do it without looking at all the numbers. We want to look at as few as possible to get to the answer. Okay. Yes, Raghu.
Thank you.
Sure.
Omkar, question about the last part of it.
Mhm.
Whether we look for kth and then k plus 1th, and or do the find the next one using the approach you talked about. Asymptotically, both are the same, correct?
Yeah, so you could find the k plus first by doing this one more time.
Okay. Okay.
Yeah. You might remember, in the sorting class, there's this problem, at least that I typically leave, finding the k nearest neighbors.
Mhm.
So there you find the kth smallest number, and then everything closer than that is already available on the left, right? When you do quick select there,
Mhm.
not
Mhm.
binary search, but quick select. So in theory, you could do quick select k times, but since you already have identified that region, um, you just gather up all that prefix or suffix or whatever it was. So this is analogous to that. Once you do it the first time, you already create that labeling and those regions, so you know exactly where the next number will lie, the successor and the predecessor.
Got it. Got it.
Okay, we can stop here if there are no more questions. Okay, thank you all.
Thanks, Omkar.
Yeah.
Thank you, Omkar.